Hello, my name is Davide Scalcon, and this talk will be about time-bin QKD experiment we have done in our lab. In quantum key distribution, there are two main state encoding used. One is polarization, that is good for free space channels, but has a problem for fiber channels that it requires active compensation of the birefingence. To generate such state, we have some good schemes that provide us good performances in terms of stability and qubit. One of those will be presented later on in this presentation. The other commonly used encoding is time-bin, so the information is encoded in the position of the photon. Those kind of states are immune to birefringence, but we need to stabilize the two interferometer needed for the preparation and measurement in order to use this kind of encoding. In this work, we wanted to use the Hyponiac, that is a polarization encoder, to generate time-bin states. Also, we wanted to try to keep the two needed interferometers totally passive, so removing all active elements from the optical paths. Also, we wanted to remove the need of external hardware for clock distribution between the two hosts. This is the overview of the setup. Everything is made of commercial fiber components and some free space elements. The system implements the 3-states 1-decoy efficient BB84 protocol. In this protocol, the key basis is chosen 90% of the time, and the two states are randomly chosen with equal probability. Instead, the control basis is chosen in 10% of the time, and only one of the two states is used. The decoy state method is implemented by varying the mean photon number of the output between two values, with a higher value sent for the 70% of the time and a lower level sent for the 13% of the time. Here I introduce the Hyponiac, that is the polarization encoder used in the experiment. The system is based on a Sagnac loop, in which the input bin splitter is substituted by a polarization bin splitter. So the horizontal and vertical components of the light will travel on the two opposite directions inside the loop. Also, the loop is asymmetric, so the two optical pulses will travel through the phase modulator in two different time instants. The halfway plate at the input of the system can be used to tune the polarization of the light at the PBS to be diagonally polarized. That means that the light will be equally splitted in the clockwise and counterclockwise direction inside the loop. By varying the phase applied by the phase modulator at the two instants in which the two components of the light travel it, we can apply a different phase to the horizontal and vertical polarization components. As you can see from the equation, we can actually generate with these systems all these states on the equator of the block sphere. So superposition of horizontal and vertical light with equal amplitude and arbitrary phase. In particular, if the electrical pulse applied to the phase modulator will induce a phase shift of pi/2, with this system we can generate the left and right circular polarized light if we apply the electrical pulse only to the clockwise or only to the counterclockwise component. Instead, if we do not apply any electrical pulse, the state will remain diagonal, so identical to the state injected into the system. This is another scheme that is used in our experiment. It's a system to convert polarization encoded states into time-bin states. It is based on a Mach-Zehnder interferometer architecture, in which one of the bin splitters is substituted by a polarization bin splitter. It is easy to see that one polarization component will travel the long paths and the other one will travel the shortest paths. So the two will be directly mapped to the two time slots of the time-bin encoding. Here the phase labeled phi A in front of the late state, represent the random phase of the interferometer that is induced by random mechanical stresses and thermal fluctuations. The same architecture of the previous slide can be used to convert time-bin states back to polarization state in a probabilistic manner. The beam splitter at the input here is labeled with FABBS, meaning fast access blocking beam splitter. This means that the beam splitter is a polarizing element and propagates only one specific polarization state aligned to a specific axis of the polarization maintaining fiber at the output. Then the BBS is used as a combiner. In this configuration, the light entering from the two ports will be mapped into two orthogonal linear polarization states at the output. So the light traveling the long path will be mapped to horizontal polarization, and the light traveling the short path will be mapped to the vertical polarization, or vice versa, depending on how the PBS is connected. Suppose we have the input, a state prepared by the interferometer that has the same path difference between the two arms. Then we can expect to measure the light in three possible time slots. The first one corresponds to the light that traveled the shortest path in both interferometers. The last one corresponds to the light that traveled the two interferometers on the long paths. The one in the middle represents the light that traveled the short path in one interferometer and the long path in the other. Working at the single photon level, detection in the early or late time slot will correspond to a measurement in the early-late basis. Instead, measuring the polarization of a photon arriving in the middle time slot corresponds to a measurement in any superposition of the early-late state. So it corresponds to a measurement of a basis on the equator of the Bloch sphere. Here I report the three outputs for the three states used in the QKD experiment. So if the input state is an early state, the state will be mapped to a superposition of the photon in the first time slot, early with vertical polarization, and of a photon in the middle time slot with horizontal polarization. If the input state is a late state, it will be mapped into a superposition of the middle slot with vertical polarization and the late slot with horizontal polarization. If the input state is a superposition of early and late, there will be four components, both the early and late with two orthogonal polarization states, and the early and late early that will fall in the middle time bin will have two orthogonal polarization states, meaning that measuring these polarization states make us able to measure the relative phase of the two components. I start now describing the experimental setup component by component. So the light source used at the transmitter is a distributed feedback laser driven at 50 MHz repetition rate, and that produces laser pulses of about 100 picoseconds through width half maximum. The amplitude of those laser pulses is then modulated by an intensity modulator based on a Sagnac loop that is used to implement the two levels decoy state protocol I mentioned before. At this point, the light polarization is modulated by the hyponiac I described before. Here, an half-wave plate and a quarter-wave plate are added in order to map the two circular polarized states into the linear horizontal and vertical polarized states with respect to the fiber axis at the output of the system. This is needed for the conversion state to work. At this point, the conversion from polarization encoding to time-bin encoding is done by the conversion stage I described before. Here below I report the 3 states it is going to generate. So the horizontal polarization will be mapped to the early state in time-bin encoding. The vertical polarization state will be mapped to the late time-bin state, and a diagonal polarization state will be mapped to the plus state in the time-bin encoding. Here, phi A is the random phase that the interferometer will introduce due to the mechanical and thermal stresses. After the time-bin encoding is done, the light will be attenuated down to the single photon level and sent through the quantum channel. The whole system is controlled by a computer. It takes care of the classical communication and of the post-processing in the key generation phase. Instead, all the electronics, so the fast electronic signals needed to control the laser and the intensity and the Ibanyak, are generated by a FPGA-based system on SOC, interfaced through the computer. Details about the architecture are available in the reference here below. The receiver side, the measurement basis choice is done passively by a 50-50 bin splitter. This bin splitter is also a polarizing bin splitter because, as I mentioned before, the light at the input of the conversion stage from time bin to polarization need to have a fixed polarization state. One of the 2 arms of this bin splitter will be sent directly to one superconductive single photodetector for time of arrival measurement, so to perform a measurement in the early-late basis. The other arm of the basis selection bin splitter is sent to the conversion stage that, as mentioned at this point, will convert time-bin states into polarization states to perform the measurement in the control basis. The output of the conversion stage is measured by this combination of a fiber polarization controller and a polarization bin splitter that sends its output to 2 superconductive single photodetectors. Now, the polarization controller here has 2 roles. It is used to fix the measurement basis in order to measure on the correct superposition of early-late, so measuring in the mutually unbiased basis with respect to the key basis. But also, it will take care of the compensation of the relative phase between the 2 interferometers used in the experiment. This is what I meant at the beginning, saying that we wanted to remove all active components from the interferometers and try to compensate the relative phase with external hardware. Here, in fact, the 2 interferometers we use are totally passive, and the way we compensate the relative phase drifting that naturally occurs is by acting on this polarization controller before the measurement polarization bin splitter. Also, must be noted that the measurement in the control basis happens only half of the times, because it is possible only if the detection happens in the middle time slot. In the other cases, the photon will arrive in the early or late time slot. Those time tags will be used as measurement in the key generating basis. The signals from the single photodetectors are collected by a time tagger, labeled here TDC, that streams the data to a computer that also manages the classical communication with the other hosts and take care of the control of the polarization controllers, the 2 polarization controllers in this setup. In this PC also runs all the post-processing of the QKD protocol. As I mentioned before, The base selection bin splitter is a fast access blocking, so a polarizing element. This is needed for the conversion stage that, as already said, it requires a precise polarization state at the input to be able to convert properly the time-bin state to polarization state. Now, that would induce polarization-dependent losses of this receiver, because the channel might randomly fluctuate and align on an orthogonal state at the input of this splitter. To prevent this and also to maintain the detection rate stable, we placed in front of the receiver this polarization controller that only maximizes the detection rate. So I want to stress out that this element is not involved in the measurement procedure. The only role it has is to keep as constant as possible the number of photons per second we can measure at the single photon detectors. One of the objectives of our experiment was to remove the need of clock distribution hardware, and to do so we modify the qubit-for-sync algorithm that is an algorithm that is able to reconstruct the transmitter clock and retrieve the information about the timing of the sent qubits, just looking at the received timestamps. And this is, as far I know, the first time someone performed a QKD experiment without having a clock distribution system. For the post-processing part, so to generate the secret key, we are using a slightly modified version of the AIT QKD software. We tested our setup on a 12-hour surround, using as a channel a 50 kilometers long single mode fiber, with additional 10 dB of attenuation. Average results are reported here. So we had 80 kilohertz of detection rate, and we were generating on average 16 kilobits per second of secret key. And the average qubit was in between 0.7 and 0.8. Here in the plot on the left, the qubit fluctuations are reported. It is possible to see that the qubit in the key basis was way more stable than the one in the control basis, and this is due to the fact that the key basis didn't need any active compensation. And the same thing can be seen in the plot on the right, where the qubit values distribution is reported. It is easy to see that the qubit distribution for the key basis is sharper than the qubit distribution of the control basis. Here is reported the secret key rate over time. Each point corresponds to an interval of more or less 80 seconds, and it is possible to see that the key generation was pretty stable over the experiment time. So, in conclusion, we proposed a QKD transmitter that relay on the conversion from polarization-encoded photons to time-bin encoded photons, and a receiver that the other way around perform its measurements, converting back some of the time-bin states to polarization states. The overall setup implements the 3-state 1-decoy QKD protocol that, while simple, guarantees us really good performances in terms of key rate. The conversion from polarization to time-bin made us able to exploit the stability and the good performances in terms of qubit of the IPONIAC polarization encoder. We think that this hybrid approach might be useful in all those cases in which the two encodings, polarization and time-bin, must coexist in a same system, like for example an hybrid free space fiber channel. Also, the system doesn't rely on external hardware to share the clock between the two hosts. Instead, in this experiment, the receiver reconstructs the transmitter clock from the time tagger data it receives. And we think this is a really great advantage because that makes the system independent from external clock sources like other fibers or GPS receivers. A preprint of this work is available on the archive, and here are the references to find it. And thank you for your attention.